Welcome, ladies and gentlemen, to this online session about boosting plant revenues with spatially resolved solar irradiation forecasting. It's quite a mouthful, but I think that you're going to really enjoy the session today. Solar irradiation is key to make sure that your solar asset, whether it's a CSP plant or a PV project, works and optimized and as optimized as possible. And as you know, solar irradiation at the ground level changes in response to conditions such as cloud cover, dust, and pollution. We have ASIs, all sky imager systems, that predict actual solar irradiation in high spatial resolution and how it will change in response to atmospheric conditions and cloud movements over the next 15 minutes. This system had already been deployed successfully in a CSP plant in Spain. As you know, CSP plants require a lot more detailed forecasting than other solar assets. But since then, new improvements have been made to irradiation forecasting technology, and it has become even more effective. And there have been a number of studies conducted that have shown that for a parabolic trough plant, you can see a revenue increase of 2%, representing hundreds of thousands of euros over the lifetime of the project. In this session today, it's a very special session because it's very, very technical. So I think that you're going to really enjoy it. And it's also going to have several presentations from leading scientists in this groundbreaking forecasting study of a tool. Therefore, it's going to last around 2 hours and is going to have copious time for questions from you, from the public, because the point of this is that you leave here with absolutely no doubt unresolved. So, for all of the questions and at mode of housekeeping, introduce yourself using the chat on the right-hand side, then make sure that you leave your questions in the Q&A box at the bottom. And we will be taking those throughout the actual session because we have some of the people who are going to be dedicated to answering that, but also we're going to be doing it at the very end. And of course, even though I have spoken quite a lot here, I'm not going to be the person who is going to be telling you about this forecasting tool. I have today with us 5 experts, 5 leading experts that are going to be telling you about it. And I'd like to ask them now to introduce themselves so that you can get to know them better if you don't know them already. So first, I'd like to ask Birk to please introduce yourself.
Yes, good day, everyone, and thanks also from my side for joining us. My name is Birk Kraas. I'm the commercial head of meteorological services at CSPservices, one of the companies who was involved in these research projects.
Excellent. Thank you very much. Birk is going to give you one of the intro presentations about the forecasting tool. Next, I'd like to ask Mark to please introduce yourself.
Yes, my name is Mark Schmitz. I'm technology director at TSK Flagsol, and I'm working in the field of CSP research for the last 20 years.
Excellent. Thank you very much, Mark. Next, I would like to ask Tim to please introduce yourself.
Yes, thank you. My name is Tim. I'm at the DLR and scientist at the DLR, and I'm working there in the part of the parabolic trough power plants and for the software development and control systems.
Excellent. Thank you, Tim. Next, Daniel, please, could you introduce yourself?
Yeah, hello, everyone. My name is Daniel Maldonado. I work for the DLR as a scientist, and my research topics are algorithms and methods for smart CSP plants, which are more efficient and less expensive.
Excellent. Thank you very much. Next, I'd like to ask Tobias to please introduce yourself.
Yes, hello, everyone. I'm Tobias Hirsch from DLR. There I'm leading a team of simulation engineers, and I had the pleasure to manage this project where we hear the results of today. And I would like to mention that this project was funded by the German Ministry of Economics. And so we would like to thank the funding we received for this. Thanks.
Thank you very much, Tobias. And last but most certainly not least, Vijan, please, if you can introduce yourself.
Hi, my name is Vijan Nouri, and I work also for the DLR. And I'm mainly occupied for the last 6 years on solar irradiance forecasting, or better nowcasting, so short-term predictions. And we do this with cameras, basically looking into the sky.
Thank you very much, guys, for coming and telling us about the state-of-the-art technology on this. It's very, very exciting. Here we are. We're taking away the screen because we're about to begin. So just a reminder that introduce yourself using the chat and to use the Q&A box at the bottom. I expect a lot of questions from you guys because this is really an equal opportunity, to ask the people who've been behind the number crunching. And these are people who've spent years, decades, studying these issues that are giving you so much grief at work every day. So just to give you a little bit about the structure. First, we're going to have a presentation from Birk. Then we're going to have another presentation from Mark and Tim. And then the final presentation from Daniel. And then we'll take questions for about 40 minutes. And we have, for that, also Tobias and Vijan adding to the answering force, so that there is absolutely no question left unanswered. Okay, without further ado, Birk, I'd like to invite you to take the mute of your microphone, please, and prepare your presentation. And you guys, from now on, just be very attentive. You've been writing down those questions. Here we are.
Yes.
Okay. Yes,
Great.
we can see it perfectly, and we can hear you. So go right ahead.
Okay, my talk is about the status of all sky imager systems and PV applications, of course, with a focus solely on the system that has been developed in our research project here. First, a small company introduction for CSP Services. We are a private engineering company, a spin-off of German Aerospace Center since 2007. We have 2 offices in Cologne and Almeria in Spain. And we work in solar projects worldwide with a team of about 25 people currently. And our scope of services is metrological services, quality control, performance testing, fluid and component services, and technical consulting generally. The content of this presentation is about the state of the art of the WOBUS system. WOBUS is the name of the research projects which led to the development of this system. So there were 2 of them, WOBUS and WOBUS R, which was the successor. Then a short excursion on the commercial product that resulted from this project. We call it QForecast. Some introduction in the underlying algorithms, so how does this system work, and few experiences from installations worldwide, so lessons learned in the field. So what is this system? It's a nowcasting system. That means it gives a forecast for a very short time horizon, some 15 to 20 minutes, and it's updated every 30 seconds, so you get a very rapid refresh. And what it can provide is irradiance maps for direct normal irradiance, for global tilted in the plane of array of PV modules, and for global horizontal irradiance. It has a very high spatial resolution. Default is 20 by 20 meters, but it can be interpolated up to 5 by 5 meters. And it can cover up to 10 by 10 kilometers area. New from WOBUS R project is that there's a merged forecast between WOBUS and persistence forecast. So persistence means you assume that the conditions that are currently prevailing, they will also be there in the future. And by doing this merge, you can get better results in certain meteorological conditions. So I just said the output are irradiance maps. So unlike many other forecasts, which just deliver you one value for, let's say, 10 minutes ahead or 1 hour ahead, here you get a whole map for the 2-dimensional resolution on the ground, so 10 by 10 kilometers, about this size. And you get one forecast value for each coordinate in this area. And in addition to this forecast value, you get an upper and lower limit with the one sigma confidence interval. These forecasts can be provided for 0 minutes ahead, so now 1 minute ahead, and so on, up to 20 minutes ahead. This is customizable, so any time that the user requires can be set. What you can do additionally, or what you can derive from these forecast maps is, for example, you can extract average irradiances over whole power plants for individual areas or subfields, or in a large area like 10 by 10 kilometers, you might have a number of individual distributed solar systems, and you can extract the average irradiance for each of them if their coordinates are known. Yeah, it's possible to do for direct, global, and global tilted radiation, and there are different data formats and interfaces possible for the output. What are the applications for such a system? You can see in this video on the right, up in the upper picture, this is the sky image that the camera sees. You can see the clouds moving past the sun. In the bottom image, you see from a nearby mountain, the area of forecast is marked in black. The green area is the area of a power plant, and red is the location of the camera and an adjacent weather station. And the right is the actual output. So there you can see the shadows of the clouds which are moving by, and you can see the DNI values that are present below these clouds. So obviously the DNI is high where there are no shadows, and they can be down to 0 under thick, large cumulus clouds. The applications for this in large-scale solar power plants is ramp prediction, and you can do a solar radiation forecast, average over the whole solar field, the distribution, where do I have how much solar radiation, or for certain subfields which are of specific interest or connected individually. You can use this for power generation forecast, ramp rate control for optimized battery lifetime, and also you can derive a power grid injection forecast. In CSP power plants, the DNI can be given for individual loops or even heliostats, and this can be used for plant operation optimization. For example, in tower plants, you could do an improved heliostat aiming strategy, knowing which heliostats will have how much DNI. In distributed solar plants, like solar clusters, this example image from Google Earth shows a solar cluster in India, which has 6 gigawatt in total. And you can see that this is distributed over a large area. This screenshot doesn't even show the whole solar cluster. And for a grid operator, this would be very interesting to know how much of this 6 gigawatt capacity will be online in the next few minutes, or if incoming clouds are having a severe impact on the grid injection. And for such large areas, multiple 2-camera systems can be combined to cover large areas. So in theory, there's no limit. You could cover a whole region. So the commercial system that is available from us, called QForecast, it's a standard basic 2-camera system. It will be customized individually for each client application. And it comes usually with an integrated weather station so that there's a reliable solar measurement input data, which is a requirement for the system. This is mostly to have a reliable source, which does not suffer from things like data interface outages or something like this. The forecasts generally can be combined with numerical weather prediction or satellite-based forecasts from third-party providers, so that the output is not limited to 15 or 20 minutes, but it can go hours or even days ahead. So now it's becoming a bit more technical, the basics of the underlying algorithms. So this is the scheme, how the system works. The first thing, it starts with sky images from minimum 2 sky imagers. Why 2 sky imagers? We will explain later. In the upper right part, you can see the sky image. In the bottom right, you can see how such a cloud camera or all sky imager looks like, in this case with a ventilation unit. And a scheme how, for example, 4 cameras can be distributed in a large CSP plant. So that's the starting point. These cameras take images every 30 seconds. And from these images, the clouds are detected and classified. So the classic image segmentation procedures are used, and a convolutional neural network approach does this segmentation to decide where is sky, where is clouds, and are these clouds in a low layer, middle layer, or high layer. And each cloud is treated individually. So each cloud is detected as an individual object which has physical properties. This is determined in the next step, cloud modeling and tracking. So here is now the explanation why it is two cameras. You get a stereoscopic view. It's like with the human eye, we have 3D vision because we have two eyes. If we had only one, then we would only have two-dimensional view. And the stereoscopic view allows to have a better estimation of the cloud height, which is quite important. Now that each cloud is detected and modeled, it can be tracked in subsequent images. And from these subsequent images, its motion vector can be determined. And this motion vector can be extrapolated in the future. Then for each individual cloud, the projection of the shadow on the ground can be done. This is a ray tracing algorithm. And depending on the height of the sun, obviously the shadow of the cloud falls on a different place. Also, the topographical information is included. And in this little illustration, you can see why it is very important to have the cloud height correct. From the ground below these two clouds, both clouds might look the same. You just have something dark right above you, and you might not be able to differentiate it. But for deciding where the shadow of this cloud falls, it's of great importance where, in which height this cloud is moving. So the improved height, cloud height estimation using the stereoscopic view of two cameras improves the location of the shadow on the ground. Then for each cloud, or for all the clouds in the image, the cloud transmittance is allocated. This is done using the ground measurement, so DNI and global horizontal irradiance. On the points where the weather stations are located, we can directly measure it. And then for all other clouds, these transmittances, so the amount of light which goes through a cloud, is distributed or allocated using a probabilistic approach. As the result of all these steps, we have the irradiance maps, which are highly resolved in space and time. As mentioned, 20 by 20 meters, and time resolution is customizable and refreshed every 30 seconds. And then in this little illustration, you can see how this looks like in a 3D model. So the clouds are moving. You can see the red motion vectors of these clouds, and on the ground, you can see how the shadows of these clouds are moving. The system has been extensively validated. There has been performance validation on multiple sites, some published in papers and conference papers, and also, of course, in unpublished sites where we have client systems, where we have also validated the performance. It's the most extensively validated system worldwide. So we are not aware of any cloud camera system which has more validation sites so far. And it has also participated in the All-Sky Imager benchmark at Plataforma Solar in the IEA PVPS Task 16. And there it fared quite well. It had the lowest mean average error in all variability classes and lowest RMSE in 5 of 7 classes. Classes here refers to conditions, how variable the solar irradiance is. These have been separated to determine how well the forecasting performance of the different systems is in different meteorological conditions. Some experiences in the field. We have installed many of these systems so far, some in southern Spain, in Portugal, several in Germany, one in the Middle East region, one in China, for example, also. And we found from the beginning that the used hardware was quite robust and resisting to different climatic conditions and extremely harsh conditions. So the same hardware that was tested in the research project went also in the commercial version with some fine adjustments and simplifications. We found that the input from using existing weather stations, which are already at place, is sometimes problematic because the data interface needs to be arranged. There may be time resolution problems because we need the input, or the system needs the input of the weather station exactly at the time when it's required. Then there are sometimes data gaps, or also data quality is an issue, as many of you may know from everyday work. So that was the lesson we learned, to integrate a weather station in the commercial version by default. Then during these research projects, we experienced the COVID-19 pandemic. So the demo systems were severely impacted by this. So we had travel restrictions, and it was not possible to travel for installing them. Also, for future or for client systems, the cost of on-site installation and commissioning are also an important factor. So this final version was designed to be possible to be installed easily by local staff of the client, and only remote commissioning by ourselves is necessary. Then we found that cleaning of the cameras and solar sensors is often insufficient in solar fields. Well, in large solar fields, you can imagine the distance between such cameras is quite large. So someone going around and cleaning several cameras, well, he has a 1 hour task, and often people do not have that much time. So we developed an artificial intelligence-based dirt detection algorithm, so that the need of cleaning the cameras can be determined with this algorithm, and unnecessary effort can be avoided. And the cleaning documentation has been improved by adding a simple push button on the systems where the operator who is cleaning them can push, and then it's always visible easily when the last cleaning has taken place. So it's easier to determine when the next cleaning should be scheduled. Yeah, this was already my talk. And thank you for your attention. And if you have any questions, then please let me hear them.
Hi, yes, Birk, I just have a couple of questions just to make sure that, everyone is like in the same page. I understand that this has been an intensive simulation study, but has there already been some testing in a real project, in a real plant?
Yes, we have several projects in commercial systems. And already in the first Robust system, we had one system installed in a 50 megawatt CSP plant in southern Spain. It was the La Africana plant, 50 megawatt parabolic trough. And the system has been in use there for several years now.
And what would be the next step in terms to a demo implementation? What are the hurdles right now for that?
The hurdles is that every project is extremely individual. The data interface is always individual. Then it must be clarified who can permit installation of such systems, who has an interest in it, and who has a use of it. Also, what is the value of it? Is the cost-benefit ratio good? So these are the main hurdles.
The cost-benefit ratio. Excellent. There was a question sent from the audience that I'd like to read to you, if I may. It says, I would like to know if there are any possibility to compute DNI from a global irradiation only, just from satellite measures.
From satellite measures?
I mean, yeah, from global radiation only. So that means without using a meteorological station, I'm guessing. So you can see it here. You can stop sharing and see it in the chat.
Yeah.
Let me do that for you. Hang on. Ah, there. Can you see it there? I would like to know if there are any possibility to compute DNI from global irradiation only.
Yes. So if this is a general question, yes, it is possible. There are algorithms or models called decomposition models. There are several published models where you can use global radiation only and calculate DNI and diffuse. Of course, it's not as accurate as a good measurement can be, but it is possible.
And just one more that has just come through, if I may. It says, are you planning to have a test in Africa in the near future?
We don't have exact plans, but we are very interested in doing it. So please contact us
Right, Moses,
directly,
so
and we can talk about it.
Excellent, Moses. You know what you gotta do. Get in touch with these guys. If you have any issues, then we can help. We can help if you guys need intros. But these guys, you can see the details also in the presentation. And I take advantage of this opportunity to remind you all that we're recording the session, that it will be available again, and that the materials will be also made available to you. So not to worry, because you'll have access to them. Next, I'd like to ask Mark to please share the presentation as we're moving on to the next presentation now. And please keep sending the questions. And just as a reminder, because I see there is a little bit of the questions go in the Q&A box at the bottom, okay? It just makes it a lot easier for us to manage them. And Mark, whenever you're ready, if you can share your screen. And for those that are on YouTube, I know there's a few people on YouTube, just send your question in the chat. We will take that and we will bring it into the room. Okay, I can see your presentation, so go right ahead, Mark.
Okay. All right, thanks, Belen. All right, hello, everybody. Birk presented the kind of scientific and technological background on this system. And I would just like to add the kind of end user perspective for the system. In the following presentations, colleagues from DLR will be going into more details on how you come from the pure meteorological view to the, let's say, thermodynamic view, which I'm referring to. So let me briefly explain why I can claim to be a user of this technology. TSK Group, of which TSK Flagsol is 100% affiliate, is a company which has been very much engaged in CSP projects, also in photovoltaics. So what we have been doing is we have been creating CSP projects all through the value chain. We've been engaged in business development. Our main field of activity is engineering, procurement, construction. So we build turnkey CSP power plants, and we've been doing so. I will be showing some references later on. Not at the core of our activity, but something which we frequently also do is the operation and maintenance of the power plants, usually the ones we have been building. This is a typical requirement by our customers, that they want to see us operating our power plants for a couple of years, maybe 1 year, maybe 5, so that they can see that all the promises we've made regarding the performance of the plants can be fulfilled. Our core technology, which we have been developing at our company, is the parabolic trough technology. Most of you will be aware that there's other technologies like the tower technology or linear Fresnel. Generally, we, as an EPC company, we build whatever the customer requires. For tower and Fresnel technology, we would have to engage technology providers into this project. So just like we don't build our own steam turbines, we don't have our own tower technology, but we would be applying this if we see that this is of advantage for a project. Also, coming back to the subject of the talk, my colleagues are going into more details where the specific advantages lie for these technologies. For myself, for this part, I will be focusing on the parabolic troughs in my little presentation. So what our company has been doing in the past is we've been developing this parabolic trough technology further. We've designed a couple of new troughs, each being more cost competitive than the ones before. And also it was Flagsol who first drafted up the idea to use a molten salt storage system in a parabolic trough field, which uses oil as a heat transfer fluid. So this seemed like a not so logic idea at the beginning, because you have to exchange heat back and forth, you lose temperatures. But in the meantime, it has become kind of the industry's standard. Just a second, get a message on
Sorry,
screen.
Mark. Yeah, could you switch on your camera because we can't see you? Don't be
okay.
shy. Here we go. Much better. Thank
no,
you.
It's,
I think
okay.
when you showed your
see my
screen, maybe something went wrong, but now we can see you. It's fine.
Okay. All right. Yeah, it's a problem with the when I share my screen, it switches off the camera automatically. I wasn't aware of that. Thanks for reminding me, Bill.
That's
all
fine.
right. So this is what we have been developing, and now let me see. This is what we have been building. So we have been engaged in a couple of power plants in the past, doing full turnkey EPC. In others, we have been engaged in certain scopes in joint ventures. You can see this is mostly the typical 50 megawatt power plant size, but we've also been building larger ones like the Ouarzazate plant in Morocco with 160 megawatts, or the 110 megawatt plant in Ashalim in Israel. For those who are not all that familiar, just one brief zoom into one of these projects. This is the first project which was built by TSK, the plant called La Africana, but situated in Spain, having 50 megawatt electric in power, having a storage system so that it can run 7 to 8 hours at almost full load into the night. And also can run all through the night at reduced load. Here also the storage system with molten salt is used to be able to achieve this performance. And well, what you can see in this picture, I think this is important for the present talk. It's a relatively large field. It has a size of about 1 kilometer by 1 kilometer. And the state of the art is that we just take the measurements of the irradiation in a very few discrete spots. So, for example, 1 or 2 meteor stations in the center, or maybe 1 on each corner, so 4 meteor stations. This is where the irradiation is measured. So for a very large part of the plant, so far we have been really blind what is actually happening. So for us as an EPC, it is really important to have such a tool in the future. This is now where what I mentioned initially, the step from radiation to thermal energy. This will be covered by a later talk. I just want to explain why we profit from it. If we know exactly how much radiation each collector gets, this means that we can adapt the temperature control much better than if we only have to react blindly to what is happening. So in the beginning, we and maybe still some other EPCs do so, assume that we have a temperature control, and so we can achieve the target outlet temperature. But in reality, this cannot be achieved when there is transient irradiation conditions in the solar field. So that means that the average temperature is always a little bit lower than what is expected. And this means that the power which can be gotten from the thermal energy will be lower. Also, the utilization of the storage system is lower than expected. Well, people who've made that experience, they say, okay, we don't achieve this, this temperature, so they just reduce it. They say, in the case of thermal oil, we target 393 degrees centigrade, but we are more safe now. We only go for 5 Kelvin less. Maybe 388 degrees. So they're on the safe side, hopefully, if there are not too many of such transients. But they, in the competitive bidding, which is now the typical business case for an EPC company in the CSP field, they let go of a lot of capacity which the storage system can hold, which is storing a certain temperature spread, and also what the turbine can do with thermal energy if it's used at the highest temperature point. So having such a tool available and the necessary experience from the past, we can now really design power plants for the meteorological conditions which are given in a site, and we know that we, under certain conditions, can meet the expected temperatures and under others not. So we can really design to the spot and make very competitive bids. It's a similar view if we look at our other activity, our smaller activity, operation and maintenance. As I said, there's only very few points where we know the real radiation so far. And we, in the past, we have been assuming that it's kind of the average of these, but homogeneous all over this field. This left a lot of blind spots. Another thing is when we operated a plant, the operators were looking out of the window and saying, oh, this looks like a clear sky or hazy sky or one with lots of intermittent cloud cover. So how to react to this was more or less under the discretion of each individual operator, which led to very different results in the output of the plant, depending on how good those people were in that job. One issue, which is maybe not so widely known, is that the thermal oil does not like high temperatures. So if there's temperatures which swings above the limit, if, for example, flow is reduced and suddenly the clouds break up, then we get over temperatures, and these lead to thermal cracking of the oil, which in turn leads to hydrogen formation, and this destroys the vacuum of the receiver tubes. So if we know better what's going on in parts of the field, this means that we can react much better and control the temperatures better. And as it has been an advantage for the EPC part of our company, so that we were more competitive in saying how much the plant would produce, we are now, as an operation company, so more competitive in getting higher revenues from such a plant, in being able to react to the real irradiation conditions at the plant. One aspect which is not utilized so far is we have lots of data in such a field. You've seen those rows of collectors. Each one is equipped with temperature sensors and other data are collected. If we have also radiation data for each collector, even if there's a certain error in it, then we can much better correlate the performance of the collector, so the temperature which it gains to what is happening in the sky, to the irradiation. So in the future, this may lead to some kind of artificial intelligence approaches to even higher plant performance. Okay, that's it. Just a little overview over what we want to do with this robust technology, with the all-sky imager, and I'm open for questions if you like.
Thank you very much, Mark. If I'm not wrong, the presentation now continues with Tim, right? And if you like, we can take the questions thereafter. So if you can stop sharing, there we go. And Tim, can I have your presentation? I do have some questions for you guys. I'm collecting them. But in the meanwhile, if we can keep going with the presentation.
All right.
Can you put that in large? Perfect. Go right ahead.
Okay. Can you see my screen?
Yes, we can see it perfectly. Thank you very much.
Okay,
and we can hear you. So
great. Okay, then thank you, Mark, from your point of view, from the industrial side. And now in this presentation, I would like to present how we can use these DNI informations and these DNI maps in this control system for parabolic draft fields to increase or to achieve a better resolution in the outlet temperature by controlling the mass flow and the solar field. First, I will give you a short introduction to our institute in the DLR. Our Institute for Solar Research is part of the German Aerospace Center, and our work is concerned with the research and development of concentrating solar power for solar thermal power plants. And in this area, all research possibilities are covered. We work from systems such as line focusing, point focusing system, but also the qualification topics, solar energy measurements, or new materials in these systems. Okay, then I will start with the presentation, how we developed a control system for parabolic draft plants. Currently, for the motivation, 6.5 gigawatt of CSP power plants are installed worldwide, and most of these consists of parabolic draft systems that use oil as a heat transfer medium. We think that it's useful to improve the control system of these parabolic draft plants in order to obtain a better overall result. The reason for this are that the control strategy used in commercial solar fields has not evolved significant in the last years. And with the development of the all-sky imager system, we can deliver much better irradiation information that can be used for control. And at least our simulation studies with these concepts have shown good results in different realistic irradiation situations. Okay. The aim of controlling a solar field is to reach the outlet temperature of usually 393 degrees in systems with oil as a heat transfer medium. And therefore you have two control systems are available for this purpose. Each collector in the solar field has a focus controller which first tracks the collectors to the sun so that the irradiation can be focused on an absorber pipe. And in a second step, a temperature controller for each collector is implemented, which controls a set point. And this means that if the temperature rises too high, the collector can be moved out of focus to prevent damage. The second part of a solar field controller is a mass flow controller for the complete solar field. That means that the loops in the solar field are set in such a way that each loop receives approximately the same mass flow. And the aim of the mass flow control is to provide enough mass flow for the solar field so that the solar field outlet temperature can be reached and all collectors are completely focused. This allows the whole solar energy to be collected. And current control systems uses 2 to 5 weather stations that can take measurements, point measurements of the irradiation. And as you can see in the picture, point measurements cannot always give an exact overview of the solar field, especially when there's a cloud over the solar field, and these point measurements may not match for the entire solar field. And this inaccuracy can lead to problems with the mass flow controller, and therefore in such transient situations, the automatic controller may be switched off and the operator adjusts the mass flow by himself. And in our approach, we have used these specially resolved DNI maps from the OSCAR imager system to have an exact overview of the current irradiation, and thus to have an improvement of the control also in the transient situation, such as cloudy conditions. For the evaluation of the control system, we compared a reference controller which only has the point DNI measurements to the new development control system which use the DNI maps and especially resolved DNI maps from the OSCAR imager. For these simulations, we used Virtual Solar Field, and Virtual Solar Field is a dynamic simulation program that models a complete solar field. The main features of Virtual Solar Field are the mass flow distribution depending on the pressure losses in each pipe element. It can model specially resolved irradiance. We can simulate flexible solar field layouts and implement different solar field controller for tests. As an example, we have here a simulated day that has a clear sky condition at the beginning and clouds in the afternoon. And here we can see that the outlet temperature from the solar field in the upper part, and we have the focusing of the solar field in the lower part. And we can see that in the first 5 to 6 hours, we can hold a set point outlet temperature of 393 degrees with the reference control system, and the focus is close to 100%. And after these 5 to 6 hours, we have a cloud in the solar field, which has an effect on the reference controller and the temperatures. Here you can see in the lower figure the curve of the irradiation on this day. And here you can see that we can hold the temperature well in this clear sky, while at the end of the day, where we have the irradiation, a different irradiation over the solar field, we could not keep the temperature at the set point outlet temperature, and we have a strong fluctuations. If the temperature in a collector rises too much, the collector is moved completely out of focus in order to protect the components and the heat transfer medium. And in the reference control, we see a strong increase of defocusing when the clouds first pass through. In the following, I would like to show how we can improve the situation with the help of the information from the OSCAR imager and these specially resolved DNI maps. Here's the slide how we use these information in the control system. This is done in our control system in 2 ways. The OSCAR imager creates these specially resolved DNI maps every 30 seconds, and we use this map to evaluate the current DNI situation. And in the first step, it is used to calculate the average DNI over the solar field, and this provides a more accurate calculation of the average DNI over the solar field, and which is used for the calculation in the control system. In the control system, this value is used to calculate a theoretical mass flow in the first step using a feed-forward controller, and to improve the adaptive calculation of the control parameters for the controllers in the second part. The second step of the use of DNI maps is to classify the irradiation. That means the current irradiation is classified into 7 classes, which cover the different possibilities that can occur. And for that, for each class, individual control parameters for the controller are then used in the respective class and which are best suited for the current situation. And with these 2 points, we can improve the control for different conditions and achieve better results. For the comparison, I have the same day as I shown before. And on the left side, the results of the reference controller are shown, while on the right side, the results with the improvements by the ALL-SCAI imager are shown. It is clearly visible that we have been able to increase the average outlet temperature, even in cloudy situation. Furthermore, it can be seen that the number of complete defocusing which occur by too high peak temperatures was reduced. These results showed that we were able to achieve an improvement in the control with the advantages of the ALL-SCAI imager system. In the last part of this presentation, I would like to talk about a robustness analysis of this control system. And we have developed a control system under, I would say, ideal conditions. So we can set and test different conditions with virtual solar field. But there are differences between the development under ideal conditions and the real solar field. Here, points such as soiling of collectors or changing solar field inlet temperature can occur. Furthermore, the ALL-SCAI imager system also has some small uncertainties when creating the DNI maps. To investigate these conditions, we have simulated and tested them in virtual solar field and evaluated how the control system reacts to these setups. We simulated the uncertainties in the ALL-SCAI imager, a change of solar field inlet temperature, soiling of collectors, and the transferability to a new solar field layout. The results I have presented here. In the setup of the simulations, we use soiling, solar field inlet, change of solar field inlet temperature, and uncertainties in the ALL-SCAI imager were simulated in combination and evaluated. The figure shows the electrical yield that we achieved with the control system. The upper area or the upper part of this figure is interesting. Here we can see the difference between the glass-based controller, which uses the ALL-SCAI imager or the informations from the ALL-SCAI imager. We see the glass-based controller with the ALL-SCAI imager to the reference controller. And on most of the simulated days, an improvement could be achieved compared to the reference controller. In general, the electrical yield could be increased by up to 2% over all simulated days. At the same time, the average solar field outlet temperature could be increased by 6% and the solar field focus by 1%. And at least on the emergency defocusing, means the collectors which are moved completely out of focus to protect the components, and the heat transfer medium was reduced by up to 48%. Finally, as a conclusion, we have investigated how these specially resolved DNI maps can improve the control of parabolic trough power plants. The specially resolved DNI maps give a better representation of the current irradiation in cloudy situations and the classification of these situations. This can lead to performance improvements compared to current control concepts. The investigations into the real behavior of such a solar field will also be able to achieve improvements compared to the reference controller. We could achieve an increase of the average outlet temperature and focus average outlet temperature and focus, and an increase of the electrical yield by up to 2% over all simulated days. All aspects from our side were analyzed from a scientific point of view, and the next step will be or needs to be a demonstration in a real plant to prove these results. For all the results of these simulations and this presentation will also be published in a solar energy paper and are then available if you're interested. Thank you for your attention, and if there are any questions, please feel free.
Belen, you have to unmute yourself.
Thank you. I was talking to myself here. Thank you very much. Could you go back to the last slide, please, Tim? Because I've got just a question or a clarification. And this beautiful blue box, which are one of my favorite whenever we talk about, you know, it's insane. An increase of the electrical yield by 2% over the lifetime of a plant is absolutely enormous amount of power extra that you can sell. You've also got like they increase average outlet temperature by 6% and solar field focus by 1%. Again, it's absolutely humongous. And decrease in emergency, the focus in events by 48%. So that means that you actually have a lot of better control over the flow of the thermal fluid in the plant. So that is great. I was just wondering whether you guys, and you might not be the right person to answer this, have done any such studies on the effect over the PV side of things. You know, when you use the same forecasting tool for a PV project, whether, you know, you see comparable results, or, you know, how do they, I don't know, not adjust, but how do they compare with this, I suppose?
That's a good question. You're right. I think I'm not the person who are able to answer this question. Maybe Birk or Mark has some, or Bishan, some answers to this question to the PV systems.
I can make a first shot, and then the others can add to that. Well, a PV system will not directly profit so much in an energy increase because it is not able to, or it does not suffer from the control problems of a parabolic trough plant, which has lots of thermal inertia, lots of runtime between different sensors. So a PV system will react instantly, no matter if there's a forecast or not. Here, the advantage would be more on the offtake side. So with very large PV plants, and Birk has been showing some very impressive examples, if the operators of such a plant don't really know what's going on in the next couple of minutes, they can really create havoc in the electric grids. So either the operator of such a plant or the grid operator will want to know when do we have to reckon with a decrease or a sudden increase in power in the grid, so that we can react to it, or that we can make from accidental dent in the irradiation a controlled ramp, so that we can allocate different energy sources for the grid. So here it is more to the energy production profile in the grid, which is of importance. So it's not so much an performance advantage, but more like a mercantile or a monetary advantage, which you will get by being able to provide energy more reliable to a forecast, which you give even at a very short notice.
Thank you very much, Mark. And I think that is increasingly important, you know, as we more and more, you know, variable energy gets into the grid, we have less and less spinning reserve, as we know. And then you start getting these really big problems. I just think that these numbers are insanely high. You know, we're talking about thousands of euros here, and over the period of like the 25 or 35 years of a project, you know, in the case of the project in Dubai, this is an enormous amount of money. So thank you very much to you both for the presentations. And then we have some more questions that we'll deal with in the end. And there's also some questions that these guys are sending from the audience. And you know, guys in the audience, you're being very quiet and very timid and very shy. Please send them through, because we have a couple more presentations and then we'll go with it. We'll go with your questions. So next is Daniel, please, if you may. You've already right ahead of me. Thank you very much, Daniel. If you can put that in large screen, please. Thank you.
Okay,
So,
can you see it in large screen?
yes, we can see it in large screen and we can hear you perfectly. So go for it.
Okay, thank you. So in the last talks, we heard about the technology, the measurement system, WOBAS, how the nowcasting data is provided by this system, and how this nowcasting data is used in parabolic trough systems. I will now talk about how we use the nowcasting data as an element for the start field operation. When we talk about the start field operation, the slide will switch.
Yeah,
okay.
There you go. It has changed. Thank you very much.
So we talk about solar tower power plants, and like this example, the Crescent Dunes plant in Nevada, and we have plant sites which are very huge. So we talk about thousands of meters. And as you can see here, the power plant, we have a lot of heliostats which reflect the direct incoming radiation on the top of the tower where the receiver is located. And in this picture, you see a very good situation where we have almost clear sky situation. So we do not have clouds passing over the field. And we ask ourselves what happens if we have clouds. So we set up our simulation tools, and on the left side you see this plant with the heliostats and the tower in the middle. On the right side you see the surface of the receiver in the center, and what is shown here is the flux density distribution in kilowatt per square meters. So now you can see a video passing clouds over the heliostat field, and what you can see is the changement of this distribution on the surface of the cylindrical receiver. What you can see is that we have a very highly dynamic system, which gives us very high demands on control and operational management. We want to control and operate the system by keeping temperature limits, also keeping limits in temperature gradients, and this is to increase the lifetime of the components. So our goal was to establish an interface between the already presented WOBAS system and our heliostat field control system to enable an optimum control of the heliostat field and the receiver. We have the WOBAS system on the left side, which is the measurement system which provides data. In the middle, we have our simulation environment, we call it Strahl. And on the right side, we have our control system, HeliOS, to control the power plant. We achieve this goal by choosing a protocol, specify the data, specifying the required commands, and then implementing on both sides the interface, the interaction between those tools. The interesting question which came up is, how do we then evaluate the WOBAS data for solar tower power plants? And the first step, we have the DNI maps already presented. We send the DNI maps to our simulation environment, so we have the correct direct normal irradiation on each heliostat. In the second step, we select an operation mode. I will go to the operation modes in my next slides. And we select this operation mode depending on the variability classes in time and in space. As you can see on the bottom, when we have highly fluctuating clouds or clouds which are very spatial in space, we switch off our power plant, and when we have something in between, we can use the conventional control, or even we can do some optimization. So the path is getting the cloud nowcaster, do the classification, determine the variability class, and do the decision about the control strategy. Let's have a look at the control strategy. Talking about the strategies, we can do this by controlling the receiver or the heliostart field. Starting with the receiver, when we have a cloud passing over the heliostart field, like on the sketch on the right side, when we look that the cloud is passing over the field and we have a conventional control, the controller detects that the incoming irradiation on the receiver decreases. Therefore, on this red line, you see that the mass flow is also decreased, which will result then in higher temperature of the salt, and the salt can also reach some areas, critical areas of the temperature, which we want to protect, or we don't want to reach these areas. Therefore, one control strategy can be that we implement so-called cloud standby. Cloud standby detects with the nowcasting data the cloud and gives us a more safe mode, which means increasing the mass flow and the right time point. This is the blue line here. So we have a decrease of the mass flow, but at a certain point we increase it, and therefore we do not reach temperatures which are critical. But the drawback is that the salt temperature of our receiver decreases a lot and we lose efficiency. Therefore, we can look for further control strategies like model predictive control, which is a control strategy which optimizes the mass flow over time. And this optimization can be such a way that the temperature of the salt is constant. So we have now a possibility with our simulation tools to look for such trajectory for the mass flow to get an optimized salt temperature over time. The second opportunity is to look at the heliostart field. There we use what we call an aim point optimization to adjust the flux density distribution directly on the receiver. That means that each heliostart aims to a certain point on the receiver to manipulate the flux density distribution on this receiver surface. That means that when we look at the pipes, for example, we adjust the aim point distribution of the starts that way that we get a constant outlet temperature of the receiver. All these scenarios, control strategies, were done theoretically, so in our simulation environment, but we also did the further step and went to a real power plant, which in this case is our testing and demonstration power plant in Germany, the solar tower in Jülich, where we have around about 2,000 heliostarts, a solar tower which is about 60 meters high. So we installed there the VOVA system. We had our simulation environment and we used our control system, control software HelioS. And we were able to demonstrate that the interaction between the VOVA system and our control system works. So we had the opportunity to analyze or to investigate on the different strategies. One was that the temperature was controlled over the receiver mass flow, you see on the button. And we also demonstrated our aim point control. So we were able to control each heliostart and the aim point on the receiver to restrict the flux density distribution in certain limits. So that's all. I thank you, and I'm open for questions for your side.
Thank you very much, Daniel. If you like, because we're going to go next into the questions, I just like to open the mic to Tobias. I know that you wanted to add us a few words, and then we launch into the questions, if I may. And this is your last chance, guys. Keep on sending them, please. We'll take them thereafter. So, Tobias, if you want to just say a few words, go right ahead.
Yes. So, thank you, Belen. So, you heard lots about details on the studies that have been done. So all about was about the all-sky imager and its application. And we can see that a lot of has been developed within this project. But still, the next step will be the implementation in a real commercial plant. And this one we have achieved for the all-sky imager systems. But the next step will be to go into a plant like the one you can see in the background here, for example, and to really use this additional information to control the plant, as Mark has mentioned, and then get all the benefits out of that. So with that, I don't want to lose too much time and leave the floor open for any questions. So we have a couple of people here answering all of the questions. So please, you're welcome to ask any question you have.
Okay, so Tobias, let me just take you off the lead because we can only see you. There we go. So why don't we start with the two questions that we had from the audience? Then I have some as well that I've come up with, and I have some that have been sent as well. So let's start with those that we have. So first it comes from Jorge and says, how the flow through the loop is controlled. So how is the flow through the loop controlled? How this control through the loop impacts the main pump's working condition. So it's the first question that you can see here in the Q&A. So who wants to take this? I'm guessing Mark, Tim, there you go.
Yes, I can answer this question. Good questions. I can say from my side, we don't control the mass flow in, especially in one loop. We control the mass flow of the whole plant. That means that we have most of the commercial plants uses some valves at the entrance of each loop, which can be manual controlled or manual changed, and these valves are used on changed in some periods over a year to establish, I would say, a hydraulic balancing over the field so that each loop gets approximately the same mass flow. And in general, in this control system we have developed, we only control the whole mass flow in the solar field at the with the main pump at its entrance.
But you may add, Tim, I may jump in and at the same time answer the second question on the simulation software that we have used for this parabolic trough simulation studies. So this is maybe first answering this question. It is a software that has been developed at DLR. It's written in C++, so for a very efficient and fast computation of large parabolic trough fields. So as Tim has mentioned in the presentation, the software is capable to represent each individual collector in the field. So we will have really 100 or 200 loops, each individually represented. And with all these collectors and loops, a hydraulic network is created with the pressure losses and so on. And then we impose a pump pressure on this hydraulic network, and all the mass flows in each individual loop are adjusted according to the hydraulic conditions. In in the studies that we have done here, it is about fixed control valves, as Tim has mentioned. So they might be adjusted manually, but they are not used for control. So all the mass flows going into the loops are a result of this hydraulic network. I think that's important to understand, because in other studies, and we can use our tool as well for these, we also study individual loop valve control. So where the valve controllers at the inlet of each loop are individually controlled to make more impact. But these ones are ongoing, but not published yet. So this may be the next step in this analysis.
So you're not done. You're still analyzing the next level. That's really pretty cool. Did you guys have like any next sort of areas of study for this tool?
Well, there are more or less, it's a tool for parabolic trough field analysis. So what we are doing currently is, we are also active with molten salt parabolic trough fields. We have just established a molten salt platform in Evora with partners together and filled there the loop with molten salt just some weeks ago. So this will be one of our next big projects to go on there. And the nice thing is that this software will be also available to the market in 2022. There will be some announcements. So all of you who want to study parabolic trough fields too may use this software and do their studies with that.
So people can actually just use the software, like it'll be available, whether there's a fee for them to use, or do they have to speak to you for you to actually run the modeling on their behalf?
No, we are planning to make this version available for the market. So we are at the moment discussing how the license conditions can be, but probably there will also be a kind of limited free version to that, so that you are able to use this. But this will be somewhere in 2022. We will come to that point.
So if I may, how do you see this tool? Like one tool just to use once the project is working, to optimize it, or you're viewing it as a possible modeling tool as well in advance of building a plant in a specific location?
Well, so far in this kind of study we have presented today, it is more about designing a plant and maybe testing control concepts that you have. So this is one application for such a tool in the end. Other applications might be condition monitoring in a real plant. We are also starting some projects in that extent, but there we do not have the results yet. But there such a model could also be helpful to better understand how the condition in the solar field really is.
Yeah, I was thinking that, right? To know, whether that's the best location, or how things may change from location to location, right? So one question here from the audience is, can you tell me the difference to other ASIs in the market? What is special about WOBAS? Who wants to answer this? Not all at once. Go, Birk.
Yes,
go for
I can answer it. The main difference is really that it's using several cameras. In the initial version, in the first WOBAS project, it was actually a 4-camera system. And so part of WOBAS A was a cost reduction by making a 2-camera system out of it. And as I said, it can be upgraded to a multiple camera system. For example, the DLR is running a weather station network in northwest of Germany, which will have, I think, 35 stations in total. In the end, all of them equipped with such cameras, so that they will have a whole network that is monitoring the sky over an area of about 100 by 100 kilometers. And this is theoretically possible, but mainly when thinking about single power plants, then really the difference to other other systems in the market is the 2-camera approach, which enhances the cloud height estimation.
Excellent. Thank you very much. You guys want to add anything? Feel free at any point. Just let me know. Daniel, are you not sure? No? Okay. Let's go to the next question. Here, Raju is asking, is there any commercial softwares available currently to study parabolic trough collectors' performance. And I'm going to send this to Tobias because probably most indicated, but feel free to name and shame so that your colleagues can answer it.
So maybe the question is a little bit unspecific because our software that we use here is a really kind of detailed dynamic software simulation tool, really for control purposes. So there are, to our knowledge, other tools out there from universities or maybe also from some software providers, but we have not seen any of these really covering the same depth and performance like ours. But maybe there is some others out there, and would be interested to hear about them. But maybe there are, you have an impression that you want to have software on studying solar field performance of a certain plant at a certain condition. And yes, for this kind of purpose, there are several tools out there, also free tools like from DLR, the Greenuse tool, or from NREL, SAM, and there are probably some others out there. So you will be able to find something depending on what you really need for your study.
Excellent. Thank you very much. My guess is there is a lot of like company-specific softwares that each company, you know, like proprietary systems, but I don't think there is much in the way of, you know, systems that you can just commercial systems that you can use and you can use for modeling. Next question is about which are the minimums for installing this software in a current operational plant? I did have this question as well, you know, to what extent is this system plug and play, meaning with what you already have, it's easy, you know, to install it. Do you have any software or any hardware needs? The software only controls the HTF main pumps based on the DNI predicted, or does it control anything else? The loops logic doesn't change. Does it change? Does it not change? So I'll leave it open for all of you guys to answer as well.
Yeah, I can start, or okay. I think there are many aspects in there. And first, I would like to recommend having a look on our Solar PACES 2021 paper, where we made some thinking about what steps would be required to install such a system in the parabolic trough field. So from the viewpoint of the all sky imagers, so what is required there, and also from the software and control part of view. I assume that your question refers to the parabolic trough application. Maybe Daniel can later on answer in terms of the tower plants. For the parabolic troughs, I think the biggest hurdle is not the all-sky imager. It's quite easy to install, as Birk has already mentioned. And it's also not the software. It has no very specific needs for hardware and so on. The main effort will be how to connect your software to your real operational plant, because in the end, the idea is that this software gives a recommendation or a mass flow recommendation and sends that out to your plant. And there's always a kind of safety concern with the plant operators. They fear that maybe they don't understand really what the software does and sends out some signals, and there is always the concern that something goes wrong with their big and very expensive plants. So I think this interface is the most crucial one, where you have to concentrate and have to spend most of your efforts at. So maybe that's from my side, and the others might add.
Birk, go right ahead.
Yeah, I would like to mention or add that for PV power plants, the situation is much easier, because as Mark already said, they PV power plants don't have these operational control issues, or even the possibility to optimize operation based on the forecasts. But the value for them is really to have a better forecast of power generation, because if you only have a point forecast, then as Tim has shown in a nice graph, You might have your point forecast or measurement in a position where you accidentally have a lot of sun, but large parts of the power plant are covered by shadows. And by averaging over the whole system, you get a much more realistic forecast of your power production. And in a market environment where the power plant operator is penalized for underproduction or even overproduction, he may avoid such penalties by doing better forecasts, for example, by acting on intraday markets and having more foresight in doing these interactions.
Daniel?
Yes, I would like to add in terms of solar tower power plants and give an overview what the software we implemented, we provide. So as I showed on my slide, we differentiate between software which is has the purpose to simulate the power plant, optimize it to make a design, and then the software we developed at the DLR, which is the control software which directly communicates between the heliostat field and then the operator. And as I showed in my presentation, we coupled them. But if you have a proposal like you're designing a power plant, you maybe look at the software Strahl, which is also commercially available from us, to do your optimization design and to go very deep into the details, how to control how the field behavior is. And when you have a power plant which is in construction, or you know that you need a control software, please contact us. Our control software Helios is adaptable for different kind of sizes and purposes of the solar tower, like different receiver technologies, heliostat technologies. We presented this software also on conferences of solar bases. Feel free to contact me, and we can discuss kind of a discussion on the software.
Excellent, thank you very much. What is the maintenance effort required during operation for this forecasting tool? Who wants to take it? Some of you are very quiet in there. I'm going to have to name. Go on,
I can
Bijan.
take it, this one. Okay. Maintenance really depends on the site. So the most important factor is really cleaning the cameras. So in order that it works, the cameras have to be cleaned, as well as the meteorological station which you're using. I think Birk said that the quality of the meteor data is important, and again, soiling of pluviometers and pyranometers is an issue. Otherwise, from that, there's not a lot of maintenance needed. So the cameras are really robust. So these are standard surveillance cameras. So they're basically designed to be outside and to be outside for a long time. And we operate some of these cameras now for 6-7 years without any issues. So yeah. And then from the software side, I think you have to distinguish between the research application which we have and then the commercial application. On the research application, we are gathering a lot of data with a high volume of data, and then it is quite quite troublesome to do all the data checks and then also to evaluate all this. I think on the commercial side you don't have that. So there you will. The system will create a certain output which is needed by the customer, and then it really depends on do you want to store it or do you want to to see it and to forget it. That really depends then on the customer. So really apart from that, there's not too much maintenance on the nowcasting.
Excellent, thank you very much. I wanted to ask, maybe this is a very kind of obvious question, and I'm sorry if it is, but how does it vary, the fact that I could be in a different geography, from using that tool? Does it have to be adapted exactly? Does it have to change? Does it have to learn my environment? Or is it literally plug and play and it doesn't matter? Who wants to take it? Oh, Bijan, you go.
Yeah. I mean, latitude can be quite important because if you're higher north or if you're closer to the equator, then you have different kinds of clouds, or you have the more important factor is that you have different kinds of demographics of cloud heights. And depending on what is the main height of the clouds, there might be another optimum of the distance between the cameras. So it is a multi-camera system. And for different latitudes or for different sites, there might be a different optimum. So it might be 500 meters for a site with really low clouds. So if you go further to the north or to the south, but if you go really, let's say to the sun belt in like 30 to, I don't know, 25, 26 degrees, then you will see more high layer clouds, or even the low layer clouds will be higher, and then you will need a larger distance between the cameras would be more from an optimum. Then another thing is turbidity. So you might have a site which a really clean atmosphere, or you might have a site with a really turbid atmosphere. And depending on that, that's what you said with learning, it could be important that the cloud segmentation has to gather new data and to learn from that. But in general, it is pretty much plug and play. It is more an optimization point. It is not that you cannot use it directly. You can use it, but there is certainly optimization potential.
Does anyone want to add anything here? No, Mark, I think you said.
No. Those guys are the experts on the on the imaging. I'm just a user of this technology. So I think
any practical approaches as to starting up in a new area, with the tool, whether you would take any measures towards making sure that it was fast and successful.
Yeah, maybe I can add something here. So some customizations, project specific, are of course there needs to be a configuration that contains like solar field coordinates. So where is the perimeter that you want to extract? Which are the coordinates that you want forecasts for? For example, in commercial systems, in a tower plant, you might want one DNI forecast value for each individual heliostat. Such configuration needs to be done, and then there's a lot of detail work in ensuring the integration into the power plant, like physically, where exactly are the plants, are the cameras installed, and how are they mounted, and who does it, and customs, importation, and such logistic challenges, and the data interface. There are lots of different data interfaces, and every project, every client is using a different one. So we can adapt to the needs of the data interfaces.
Excellent. Thank you very much for clarifying, Birk. A question for you, Mark. As an EPC, do you see the benefits in winning new projects when you use these ASI forecasting tools?
Yes, definitely. Of course, the improvements which you can gain energy-wise, as explained by DLR, in those examples were 2%. Maybe to some of the audience that does not sound like it's such a big number. You emphasized that it is a big leap. And
I like to put euro signs next to it, but I don't know what they are. But if you have some euro signs, do say it, because I think maybe it's not so obvious when you see 2%.
Yeah, I think what you just have to imagine is if you look at those aerial photographs of those parabolic trough fields, they cover land of 1 kilometer by 1 kilometer, and they have something like 150 loops of collectors, each a couple of 100 meters long. And adding a performance of 2% means it's equivalent to adding 2% or like 3 such collector rows or some kilometers of collector rows is an equivalent amount of energy which you can gain. So there you quickly talk about a couple of million of euros in equivalent investment. And if on the other hand, you look at this camera, which is nothing more than a security camera, which is hanging in every a grocery store on the ceiling, then you can see that it's really a no-brainer to use this to make your project much more cost efficient.
the cost opportunity seems pretty huge then. If like the investment is not very high for what you get.
Exactly. Yeah. I think it's really strange. Well, this system is relatively new, so that's maybe one reason why there's no high market penetration yet. The other aspect is that operators of such plants, they shy very much investing into their plants. It's something which for a company which is building new plants is not really comprehensible why there's such a reluctance to invest a couple of euros into their plants to give a higher output. But we've realized that even investments which pay back in a few weeks or months, they are not done because people are shy to put money on the table. And it's something which is known in the community and nobody understands really. But
it's difficult, right? It's difficult to explain the energy efficiency, how much money you can save. I mean, a good option, I think the PV community might be a little bit faster than the CSP community in this regard. For example, with bifacial panels, this is something that, it adds a little bit of cost. It's more complicated in terms of the VOP or the VOS of the plant. Yet we're seeing, moving towards, bifacial panels because the gain overall is a lot better. But it took years and years. I think deployment size may have something to do with it. This is just my opinion, because with CSP, you would have to, if you were building one, every month, so to speak, then you would be getting them better and better and better and better. But otherwise, the reluctance is there. I just have a question for Birk. Can you gather the data from an ASI installed somewhere in the world and literally view and optimize and look at and study the numbers in your office somewhere else in the world?
Yes. Like any other webcam, you can access the camera images from anywhere. So it's exactly what we've done in the demo system in the Robustness project. We didn't put the evaluation computer, which runs this software that analyzes the images and does all these steps that I have presented. So we didn't put this computer in the project site, but only the cameras. And we accessed the cameras from our office and transmitted the images. And it mainly depends on the interface and the internet connection on site. So how exactly is it done with a 4G modem or with cable access? So yeah, technically it's not a big issue.
And guys, does this learn by itself? Does it become better with time? Is it got the machine learning / AI thing that everyone talks about, or how does it work? Is it a closed system?
Bijan, I think you are best prepared to answer this.
It doesn't learn by itself. So it is right now. It's a closed system. So we are continuously working on a development, and we are gathering more data, and we are getting better. But if you would put a system somewhere, it will stay at the same state, and there's not like an automatic learning, or it does not happen yet. But it is quite interesting. So yeah.
This is what everyone talks about right now, right? Like
reinforcement learning. Yeah, reinforcement learning could be interesting. I don't know, but right now
it might not be necessary. I just wonder,
it could be quite interesting, but it is not done.
So a lot of, for example, the tools that are not deployed in PV, O&M, the softwares, like they're talking a lot about, making them better, but also learn themselves so that they become increasingly good at predictive maintenance, which, saves you a lot of money over time. It's one of the latest PV projects, they barely ever fail, or anything barely ever fails because it's always maintained in advance. I mean, you guys know this better than I do, but this is what I find really interesting, when you can stop problems before they occur. So I have another question about implementing the system. How long does it take to implement a 2-camera system? Anyone? Birk, maybe? Yep.
Yeah, actually not very long. The hardware, as was mentioned several times, it's more or less a camera, a standard camera and a weather station. So if no reliable weather station is already on site, then this is the most time-consuming hardware part. And then it's the logistics challenges like shipping internationally, customs clearance, importation. The system itself, its installation is done within a few hours. It's really simple to install. and then integration into the power plant data interfaces. So several weeks plus shipping and customs clearance times.
And can I ask you, is this like an IKEA set that you come and with these really terrible instructions, you can still make it and you can sit on the chair without breaking? Or do you need someone who actually knows the system, like one of you guys or someone who's taking a course or something to go and install it and prepare it?
For the installation itself, the hands-on work, no, it's very simple. So it has been done like this in the demonstration project. We just sent an installation manual with step-by-step instructions, and it worked out flawlessly.
Excellent. That's really great, because you could ship it anywhere in the world. It makes it so much easier because the barriers of entry are so low. Why do you need a weather station? And is it shipped together with the cameras?
It was one of the lessons learned from demonstration projects. So several factors contribute there. One is the data interface. Not every weather station that is already operating might have a suitable data interface that interacts with the system. Sometimes data interfaces are not reliable, or the time resolution of the measurements done are not suitable to interact with the system. And also quality is sometimes an issue. It's having an own weather station allows a good estimation of the data quality, because in our weather station, we know that the quality of the sensors, and we know the required maintenance routines, and we can judge the quality very much better.
Thank you very much. And earlier I asked a question, to the CSP guides, how is this working in PV projects in terms of this 2% that we were talking about? I want to open it up to the rest of the group. How does it work in terms of cost opportunity for PV projects? I understand that the cost itself is really quite low, but what is it that you win? You guys did make a really interesting point about sort of managing different assets, in like kind of in a line as a TSO or as a, but what can you tell me about the PV side of things? How can I see, a value cost opportunity here? So I don't know who would be the right person to ask, by the way.
Maybe I can say something.
Go for it.
There's no general answer to it, because every power plant is really individual. Many plants have their individual PPA, power purchase agreement, where it's defined whether they even need a forecast, or how the forecast must be, and what is the consequence of wrong forecasts or inaccurate forecasts. And then there are a lot of plants who don't have to provide a forecast. Like most PV systems in Germany, they just get a fixed feed-in tariff. They provide no forecast to the grid operator, so they have obviously no need for such a system. But once you are in a market environment where you need to provide forecasts, and you need to provide accurate forecasts, and otherwise it costs you money, then this gets very interesting, because the investment cost for this system is very low, as mentioned several times. And if you have a multi megawatts, like 200, 400, 500 megawatt power plants, then penalties for inaccurate forecasts can be in the range of tens of thousands per day. So such a system would pay off within several weeks.
Is it used, or can be used, to predict overheating in panels, in PV panels, particularly in desert areas and places where the temperature is higher than PV panels usually do well with? Or could it be adapted, I suppose, the question?
It would require a subsequent model that uses the irradiance information to convert it to expected module temperatures. But generally, yes, such a use is also possible.
I was wondering, because it seems that overheating in certain markets is a big issue, and cooling systems aren't great. So if you could predict this in advance, it could make a huge difference as opposed to the managing of the projects themselves. I don't know if anyone wants to add anything here. And a question for TSK again. You're investing in molten salt parabolic trough plants. I can't wait to see one of those, by the way, Mark. You know, I'm looking forward to you guys building one. Do you see specific benefits for molten salt units compared to traditional oil plants?
Well, good question. We've been involved in both technology development, the forecast system here, and the molten salt in troughs. In general, I would say molten salt collectors are less prone to overheating because the fluid is not driven to its maximum temperature, and the results of overheating, I've mentioned in my presentation, the formation of hydrogen, which is very destructive. This does not happen with molten salt. So if it overheats, a certain reaction will take place, but it will reverse itself over time. It could be that the effects are not so pronounced for molten salt as for oil plants. But I don't know. Tobias here mentioned already the molten salt topic as one future outlook. Maybe he has another view on this. I would say it's slightly less the impact.
Go on, Tobias.
Yeah, well, this is, as you mentioned, a kind of topic for research. So we think there might be benefits, especially if we go with these loopwise valve controls. So having an information on the irradiance of each individual loop might help to control these things. But still, we have to figure out that. And maybe if we go to higher temperatures and also to the limits, it might be interesting, but maybe it's too early to answer that question at the moment.
And the one question that we got from YouTube is, did you consider the effect of dust or pollution? This is particularly important in the desert areas, you know, where there are things like sandstorms. I get that this is not weather forecasting, but it is not less important. And perhaps, you know, over time, these models could become better and better. So I don't know who wants to take this. I'm looking at Birk all the time, but he probably... Birk, do you want to go and answer this?
Yes. Well, the system is really meant to monitor clouds. We have not investigated specifically a case where a sandstorm was observed. It may have happened that our demo system or test system in the Middle East region actually experienced one, but we haven't so far taken a look on whether this could have been, there could have been a pre-warning of an incoming sandstorm front or something like this.
What I can tell you is you can see it in Dubai, you know, the suspension in the air. So for me, that has to be worse than clouds sometimes. Sorry, Mark, I interrupted you. I didn't mean to.
No problem. I just wanted to add that Birk also presented that there was an soiling detection mechanism or algorithm conceived for this camera system, so that it only has to be cleaned when it's dirty. I mean, one side effect of this is when the camera is dirty, you can well assume also that the solar field is dirty. So maybe this can also be used as a soiling detection mechanism for the photovoltaic system or the parabolic trough collectors or heliostats, whatever is there to collect the energy. So possibly this is a side use of this thing.
Okay, so this is an interesting debate actually, whether this could be adapted, because I think it may be useful. Depends again, right, on the place in the geography. Mm-hmm. We've got two more questions, so we're gonna answer them right away. Okay, one actually continues on this. It says, dust, soiling, and smoke, as in California. This is a good point. Does something like smoke also change the way it works?
I think it's the same like dust. We haven't specifically analyzed it. Bijan, maybe you have some further comment on it?
I mean, in terms of smoke detection, when it's about wildfires, there are already quite a lot of commercial products, I think. And I think in the presentation from Birk, you could see this. I mean, you wouldn't use this sky camera. You would more use these cameras on an evaluated position, which are looking down. So we had this camera on the mountaintop, which were looking down on the ground. And from these kind of cameras, there are commercial products for smoke detection. I'm pretty sure about that. In terms of detecting dust storms, yeah, I haven't seen any in our data yet on all the sites. So we never looked into it. I would say, okay, if you have the cameras, then and you have an operator, you could maybe see them in advance for a couple minutes, but that's then really manual detection. In terms of automatic detection, yeah, there's certainly a potential, but as I said, we haven't looked into it.
Yeah, I think if you have in mind those images of really those very discrete forms of sandstorm, the haboobs, as they are known in like the Arab region, they really form a high wall of dust, which could be well detected by the camera system and lead not really to energy saving of the plant or optimization, but to just put the collectors in such a way that they don't collect too much dust in the event of this sandstorm. So I think in some regions, these sandstorms are quite so frequent that they really mess up the optics of the solar field for weeks to come, because it's not so easy to clean such a large field. So it's maybe a good idea to detect such a thing early on and put the collectors in the safety position.
I think you have to keep in mind that the distance you can look with these cameras. So I'm not sure what, well, you probably, if you have a couple of minutes in advance, then you can go to the safety position. Okay, that I understand. But that's really what you can see. It's you might get the information in advance 4 or 5 minutes, and that's it. It's you cannot, because the line of sight is really limited. So especially if they are low, I don't know which height do you have these sunstorms.
I think 1 or 2 miles high, and they travel not too fast, really.
Okay, then so then you can see them when they're around 4 kilometers in distance, and then whatever time it takes them to travel these 4 kilometers to the power plant, if they are traveling in direction to the power plant, that's then you.
Right.
You guys, we're finding a lot more work for you to do, you know, for the next versions of the software. So this is not bad, I think. Okay, there is one more question. Luai asks Mark, the flexible joints and interconnectors currently are able to withstand the maximum temperature of the molten salt in case of the parabolic trough collectors. That's correct, right? That is like the stress point or the ball joints.
Yes, in 2 ways. Firstly, there's with the molten salt, there's a chemical attack, corrosion. That's a problem. Then the higher temperatures is another issue. And also, as a side effect of the higher temperature, the thermal expansion becomes bigger. So this the movement of the thing with being hot or cold is much larger than in a conventional plant. So this is a technological challenge, but there are solutions for that with flexible hoses. That's the most reliable one we've found so far. With ball joint, the problem is that I'm only aware of systems which use graphite as a sealant, and graphite reacts with nitrates, so this will not work. So, but flexible hoses is a solution.
Excellent. Thank you very much, Mark. Do you guys want to add anything else? I think we asked a lot of questions, but I just want to make sure. Tobias, do you want to ask anything? Yeah.
I think I would like to applaud the audience, because there have been very good questions, and I've been in other talks where it was just silence after the talk, and I appreciate that very much, that this has been so much of a dialogue, and so thank you to the audience.
Thank you very much, Mark. What about you guys, Tobias?
Yes, I can only follow up with Mark. So I think it was very interesting, and many of you stayed these 2 hours. So if I look on the number of participants, still many in there in this call. So it was, I suppose it was interesting for you, and I hope it was interesting. And if you have more questions, I think you will find our email addresses somewhere, and feel free to contact us. And also thank you, Belen, for very well moderating through these 2 hours. So thank you very much. From my side.
Thank you very much, everyone. Okay, so this has been a very interesting talk. It was very technical, so I do my best to keep up. Let's be honest, these guys are the guys that know about the technical side, and these are the guys you need to talk to if you have some questions, because I'm not going to be able to answer those for you. However, when it comes to the market, I do understand the value of these tools. Mark made a great point, which is usually we don't take these kind of technologies into our business models. You know, we go for the stuff that we need to make something work, you know, particularly when it comes to a technology like CSP. You know, you have one plant, one project every so often, you know, they're not so numerous, you know, that you kind of keep the learning going from one to the next, sadly. The case for PV is slightly different. However, the case for PV is gaining so much more in strength. I am going to take the case of Spain, but it's not the only case, so that just to explain my point. In Spain now, in the next 10 years, we're going to build 30 gigawatts worth of PV projects. This is in a country where peak power needs are about 31, 32 gig. So you can imagine at 12 o'clock, if it's a sunny day, you're going to be creating and generating an immense amount of power. The only way for you to be able to manage that and to manage curtailment when you have storage is to have this kind of forecast tool, to be able to, as a whole, with all of your assets, know when you can take the power, when you can store it, when you can release it. This is the same for CSP, by the way, but I just want to make sure that you guys understand that over time, these kind of forecasting tools are going to be so important to your business models, more important than any other time, because you're going to have to know, and you're going to have to be able to understand not only how your own projects are doing, but how everyone else is doing, and how you can react, and how you can hedge your bets, because as the market is liberalizing, you know, things are going to become more in a play that each of the assets is going to be betting in pricing. And as, you know, energy storage becomes more omnipresent, if you like, you know, you're going to have to get cleverer when you take in the power and when you release it. So understanding the weather is so important. So if you're on the PV side of things, you need to talk to these guys. If you're on the CSP side of things, you need to talk to these guys, but you probably already know them. So I just hope that you realize that even though, you know, the case right now may be a little bit strange and a little bit, you know, I don't quite understand it. This is only the beginning. You know, in 5 years' time, you're going to be begging for the understanding how these modeling tools work, because it's only going to get more and more complex, if you like, over time. So I hope that you guys enjoyed it. Thank you very much to the audience, and thank you very much to all of you. It's been a really great session. Thank you, Birk. Thank you, Tobias, very much. Thank you, Daniel. Thank you, Tim. Thank you, Vijan, and thank you, Mark. And we will see you in the next session. Thank you very much.